Okay, I don't know how to fix the screen, and I think we have already wasted enough time. So I am going to try it again, but if it doesn't work, we just proceed. Yeah, I can't fix it, so we'll just focus on that screen. So the first thing that I wanted to cover, which we didn't get time last time, was this idea of the generalized linear models. We actually didn't visualize it. We didn't really do anything, even though we had um, covered it. The simplest GLM is actually, of course, your logistic regression model. And the simple idea behind logistic regression is your yi can only take values for just two values, which is 0 or 1. And what we are trying to do is we are trying to fit a curve which tries to estimate this relationship. And in this sense, happens to be the logistic regression, of course, is the first uh, one of the first few ways that you can think about it. Your outcomes are binary, and to capture those binary outcomes, you can only take discrete values. This happens to be 0 and 1. What we model there is this pi I, which is just the probability of yi to be 1. What is the probability that this is 1? To model this, we model the logic, right? So this is your mean function, and the log of this, right? The log of this mean function is a linear model. Okay. This is the central idea behind generalized linear models, that a function of your mean, some g of mu, is beta naught plus beta 1 plus beta xi and so on. And in this case, the link function happens to be your log or logic function. If you expand this, you can first write this formula, and this is where your logistic regression formula comes out to be, which is p y equal to 1 is x of beta sigma beta I plus 1 plus divided by 1 plus x of sigma beta. You can also calculate the odds ratio, which is what is the probability of one event happening over the other, which is pyi equal to 1 divided by pyi equal to 0. And of course, in some sense, you would have either seen or used this kind of formula at some point. So we will try to actually use this in real life. Very, very simple, right? Like it's a yes or a no or a 1 or a 0 kind of a condition. So imagine there is a proportion where you have measured uh, if snoring is related to heart disease, or what is the relationship between snoring and getting a heart disease. There are different categories of snoring. You never snore, you occasionally snore, or you nearly every night. And how many of them have been detected to have a heart disease, right? So this is a 1 and this is a 0, and this is the proportion of yes. The simplest question that I'm asking is, what is the relationship between snoring and getting a heart disease? How would you model this? What would you think about? What would be the simplest model to explain these observations? Okay, association. So in what sense? You either get a heart disease or okay, you could do a proportional chi-square kind of a test. What is your null hypothesis? There is no association between all of them. What if I ask you that you can assign a numeric value to your snoring levels? So 0 is no snoring. 2 is occasional. 4 is nearly every night, and 5 is every night. Then how would you try to test this? So my null hypothesis, of course, is there is no association, and that is what your null hypothesis will capture. Any other things that you can model with?
Use the logistic regression and just
Yeah, we can, of course. I mean, logistic regression. You're saying it because I started my lecture by talking about logistic regression, but I could have just done what is the relationship, right? Like, what is the proportion of yeses, right? I could model just the proportion of yeses as well, which is a continuous value. 0.01, 0.055, 0.099, and again, always plot your data to see how does that relationship lie. But of course, we know that this data overall, we have more information if you don't collapse it into proportions, because 24 by 1355 versus, let's say, 240 by 13550 will give you the same proportion, but of course you have more power and more information if this number was high. 240, 13550. So if I multiply everything by 10, proportion remains the same, but the amount of information I have is actually nearly 10 times. And you want a model to be able to capture that in essence. And that's what we will hope to do with our data. Yeah.
Is there any reason there's no one in the zero?
No, this is arbitrary. This could have been. There's no reason as such. It could have been one as well. It just felt to keep it slightly away from one. That's all. Okay. So this is taken from a paper, and what we are going to do is we will try to. Sorry, that's not relevant. We will try to model it using. So if you go to the website, um, if you go to the website, sorry, I have too many windows open today. Okay. If you go to this website, the course website, the first URL is um, your URL for the snoring example. So I'm going to download this. It's a QML, it's a RMD file, and if you download this, you'll have it wherever you want. But I have it downloaded somewhere. So the first set of code here is what we're going to do is we will try to fit this linear model, and then we'll try to fit on a GLM, and we'll see and we'll try to compare which model is a good fit overall. Okay. So what I've done here is I've just converted these values into a linear model, or into a setting. So I will change around things as we go along. But in the first set of code, all you're doing is you're fitting this as a linear model, right? So this is what it looks like. Just 1 second. Okay. Um, So in the first part, I am just modeling as a function of what is happening, right? So on your x-axis is your snoring scores, and on your y-axis is the proportion of yeses that you see. So you can see that it kind of is linear in some sense. But is it the best model, or is it the right sort of way to model this problem? We will try to answer that question by fitting what's called a logistic regression model here. So I'm taking the same data, but now rather than inputting the proportions, I'm inputting yeses and nos. I am creating a frame here. Again, I'm coding these values to be 0, 2, 4, and 5 from the data frame, and I'm then running a GLM model here, right? So the GLM model is what is the proportion of yes as a function of your snoring scores, where your data frame is this here, and this weights, right? So if you see in the model, I'm actually still fitting proportion yes, but I have to, of course, pass it the information that I know that this proportion is not based on just 1 or 5 or 10 values. The total number of values that I have for each column, that is my total column. Right? So the total is simply the total of 1355 24, 35 603, 21 192, 32 24. You're telling it that while the proportions could be something, you should weigh the totals, or we should weigh each reading by the amount of information that you have, and that information comes from the total value. Okay, so this total is simply yes plus no. Okay, that's how you fit a GLM in R. So we will do this and let's see what it looks like. And at the bottom, what I'm doing is I'm plotting the same model. I'm plotting the logistic regression against the linear model and trying to see what is really different. What is it that it's trying to fit? So this is your actual observation, the blue point that you see in terms of your proportion SS. The blue curve, the red curve here is the linear model that we got, and you see it. It kind of fits actually pretty nice. What happens in the case of logistic regression is, of course, this function when visualized in the actual space is not linear. It's in some sense non-linear because you have captured the non-linearity from the logic function, and that's what you see here, right? So overall, you can see that these two models are different, of course, right? If you're fitting on the same values, you're fitting two different models. One is logic, one is linear. Now, the natural question to ask is okay, you can do whatever you want, but is this a good model overall or not? Or what is the measure of this being a good model overall? And we will see how to quantify this. So, very briefly, how to quantify the fit of a model is by using this criteria of the archaic information criterion. AIC, and there is a corresponding version in Bayesian world which is called BIC, Bayesian Information Criterion. We'll focus on the archaic version. It very briefly measures how good is your model by measuring the likelihood. Right. So the log likelihood of any model is given these observations and given your model of choice. What is the total likelihood of observing it? In this process, what we do is we learn the parameters. Once you learn the parameters, you can quantify what is the likelihood of observing this. So, how do we assess whether one model is a good fit versus the other? Is by simply running AIC on two models, right? So, I had a fit.lm and a fit.glm. That's the only function I need to run. And what it tells me is the number of degrees of freedom are different for both of them. And overall, what it is telling you in this case is the linear model, which has lesser archaic information criterion, and the fit GLM has some 27 value, right? The scale here is not, it's not something that you want to care about. What you care about is between these two models, what is a good fit. And this is a bad example to motivate logistic regression because it seems so the lower information in AIC is what is preferred because it's the minus log likelihood. So in this case, this happens to be your linear model is actually a good model, and you can see that, right? Like so, there is if the model if the final information that you're getting is telling you that you don't require the complexity of a GLM, you don't require it. So as long as whatever your data is, if you can fit a linear model, that's great. But in this case, that's what happens. While this example was to motivate a nonlinear model or a GLM, not a nonlinear model, but a GLM, it appears that linear model is doing a decent job. So I would probably just pick it. There's no explicit advantage right now that I see of fitting a logistic regression model. Okay, so it's a very context dependent thing. So use it with caution, in the sense that sometimes you really have ideas or you really have hypotheses about something that you really think has an association to your outcome variable, which you should explicitly account for. It can happen that your AIC value changes from 5 to, let's say, 6, but this seems like a more plausible model that you have. You're going to go for it. Yes. Sure. So I'm going to switch over to the slides and I'm going to talk about what is this AIC metric. So the AIC metric is nothing but the log likelihood of your data, the minus log likelihood of your data plus the number of parameters that you're fitting. Right. So this is your DF that you saw in the degrees of freedom that you have. Right. So the number of parameters that you fit for a logistic regression is beta 0, beta 1. In the case of linear fashion, it's beta 0 or beta 1. And here, once you've learned those parameters, you're trying to calculate what is the likelihood of observing the data that you do. In a sense, that if you have learned the parameters correctly, right? If you have learned these parameters correctly, then you will get a lower value for a higher value for this, which means an overall lower value. That's the intuition. If you get the parameters right, your likelihood of observing it will be high. But since there is a negative sign, you want it to be in the other direction. So you want this to be lower value. That's what the intuition is. Now, how does it actually relate? Like, what is it that we're trying to do? Right? So, if you've heard about this model, this bias variance trade-off, I can have a very complicated model. For example, this one, right? Like the red one here is very complicated because it tries to fit the data perfect. But in the process that I'm trying to fit this, I will have a high amount of variance. That is, right? In terms of while it is able to fit each and every point correctly, or it's trying to do that, but there is a lot of variation in terms of that process. In a sense, like there's a sweet point between making a model very complicated and making it generalized. Your goal is to be able to capture both. Your model should be a good fit to the data, but it should also be generalizable. Right? So, for example, in this case, this is a very highly biased model in the sense that this model that you're seeing here, the green one, if you calculate the differences from the observed values, you're going to get very high numbers, right? So it has a very high bias, but the variance is not too much because everything is constant, right? So there is no variance. Whereas in this case, the bias is going to be low, but the variance is going to be very high, just because there is too much uh, Zigbee pattern that it is following. The goal of AIC is to find a sweet spot. That's why this function is adjusting for the bias that you have, and this function is adjusting for the variance that you have in terms of the complicated number of points. So the more parameters I have, right? So logistic regression is like one. If you're just doing it with this, you just have beta 0 and beta 1. But if I wanted, I could have made it complicated by saying that there is beta 0, beta 1, x plus beta 2 x squared to be a really good fit. But do I require that complexity? That is something that the AIC tries to answer because it will learn these parameters and it will say that okay, this is your likelihood of observing it. But this parameter has higher number of this model has higher number of parameters. So I have to account for that explicitly that you took extra amount of effort to calculate it, and that's why your log likelihood can be higher, right? In some sense. To do that, you adjust that value by 2 times the number of parameters that you have. Log likelihood of your observations, right? So your yi is your x of yi is being modeled as the logic of this is being modeled as a linear model, right? So you can calculate what is beta 0, beta 1, and then you can calculate what is the likelihood of observing your yi's based on this one, where your function follows a log, uh, is log distributed. Very simply, for example, very simply, in the case of normal distribution, you learn the mu and the sigma square, right? Let's say you did beta 0 and plus beta 1 x, where this is y. So I've learned what is beta 0, I've learned what is beta y. Then I'm going to calculate based on this what is, I will multiply for each of my y observations, which this stands for multiplication, 1 to n, what is my x beta I and what is your sigma. You will multiply this value for all your yi observations. Okay? That is your log line. And you're going to substitute yi value in each of them because there is a formula. We don't have to do it explicitly for this class because this is supposed to be an introductory class, but we will use R for calculating the log likelihood. Okay? Log likelihood is nothing. Once you've learned the parameters, what is the likelihood, which means what is the probability density function of this value that is seen, right? So your yi is supposed to be distributed like this. If you're doing a Gaussian distribution, I know the parameters of this distribution, mu and sigma square. Essentially, I'm calculating what is if my yi is this, I'm calculating what is this value, and if I have another yi, I'm calculating what is this value and multiplying these two. That's it. That's what your likelihood is. Okay. How probable is it that you get observations yi1, y1, y2, and yn? That's what you're trying to essentially capture. Any questions about log likelihood? Any questions about? Is it clear? Okay. Um, so this is something which we did not cover, and you've seen this version. Sorry, you have seen this version in one sense or the other. Is once you have access to your if your data has um, account structure, then the model that you usually use is Poisson or negative binomial. So one distinction which we didn't cover in the class, and I don't think it's very important, is what is the mean and the variance, right? So if this is a Poisson distribution, its mean and its variance are actually the same, right? When you fit a normal distribution, that mu and sigma square have no relationship, right? So if I plot the relationship between mean and variance, for Gaussian, it's going to be flat because they're not related at all, right? There are two different parameters. But in Poisson, there is only one single parameter that you're trying to learn. But because of this, there is an increasing relationship. If the mean lambda increases, the variance of that particular Poisson also increases. Okay. Now, what happens, unfortunately, sometimes is a lot of data that we observe, the mean and the variance are not going to be equal, right? Okay, so this is your Poisson line, which is y equal to x, because its mean is lambda, its variance is lambda. It is lambda because we can derive it, but for this class we're not going to derive it. But you can assume that mean and variance are the same for Poisson. However, in the case of a lot of real data, this does not hold. What will happen is when you calculate, for example, let's take the example of COVID cases. If I calculate the COVID cases in the entire country, right, in different states, for example, and if I calculate on a mean basis, on a daily basis, that today mean of the entire country is 100, tomorrow it's 200, and then maybe it's 350, and if I plot it against the variance that I see in the country, then I will see that the variance is very high actually. Maybe 1,000 or 2,000 and maybe 10,000. So you'll get values like this, where the mean of your observed variables is not equal to the variance. And that's when a Poisson model, which is actually designed for counts data, is not sufficient. And that's when you switch to negative binomial NB model. Why is it called negative binomial? Is a homework exercise, which we will not do this in this class because it requires some derivation. But it's called negative binomial for a reason. Okay. So counts data, anytime you see Poisson is your default. Poisson usually will not fit, and you will have to use negative binomial data, negative binomial fit. Okay. Any questions? No questions. Okay. Okay. Then very quickly we want to talk about the interaction effect. Okay. So let me download the data. This is best taught using an example. Um, so if you go again to the website, you will see there is a second lecture here. I have lost my website, but if I go back, there's a second session here, which will download the interaction effect notebook for you. Okay, so download that notebook and we'll walk over it, and maybe I will have it ready so that we can see what happens overall. So this is taken from kind of a simulated data. Let me first show you the data. So overall, what I'm plotting here is just the effect of cholesterol. Effect of what are called these drugs, magic drugs called statins. Uh, on the x-axis, their dosage, and on the y-axis is your cholesterol. Right? So statins are a special kind of drugs separated initially from fungi, which allow you to control the level of statins, the cholesterol in your body. Right. So a lot of Indian population is actually predisposed to have high cholesterol. They should be on statins. It's one of those drugs which quote, can be mixed in water and everybody should be having it. It's not fully true. It has its own side effects. Um, but I think if you have, or if you know somebody in your family who has high cholesterol, ask them to consult your doctor. But this works. I can tell you from first hand usage. I'm on statins for other reasons, but yeah, I think it's useful. It gives you certain side effects, but which usually involves some sort of muscular pain, but it's not for everyone. As in, it doesn't happen to everyone. So, but it helps you control your cholesterol. Okay. Um, so what I'm showing you here is this curve here. What patterns do you see? All values here are of course are hypothetical. These are not taken from any study. And I am going to hide this because this is only going to be relevant later on. Okay. So I gave you this kind of data. What is the first thought that comes to your mind? Like what kind of model? Yeah. Yeah. See. Good. Yes, sir. Yes, sir. It is. Yeah, the cholesterol level is decreasing, right? So in essence, what is happening is the there's a negative correlation or there's a negative relationship between the amount of dosage that you have and the amount of cholesterol that the body is detecting. Again, these are hypothetical. This is just to motivate. Okay, so that's what this plot shows you here, that this is the usage that you have. So what is the first model that you're going to fit here? A simple linear model, right? Like for example, let me show you. But one more information I'm going to tell you is that there is, of course, there is something for males and there is something for females. Now, with this information revealed, what kind of model would you fit? So there is some data for females and there is some data for males. Sorry. Okay. So what would your model look like? Mhm. Okay, since we're not using it as a screen. Okay. Y is equal to and
So one would be for the male and male will be categorical, so it will add to the intercept, and
hmm.
X should be my dosage. Beta not will check. It will be kind of parallels, but not exactly.
Okay. So one model for this is female and one model for males. So you mean this this model? We don't want to say. Okay. So this is option number one. Option number two is so intercept is changing, slope is constant. Which okay. And any other options?
You can combine it in a single
So you
equation.
can add a new variable gender.
Okay. I can add a one. Oh, yeah. Okay.
So gender and the dosage seem to be affecting dose.
Gender and dosage seem to be affecting the cholesterol.
So it took a peek on the next slide. So
Okay, that's fine. Of course, that's my mistake. So yes, it's good. It's good to think then. Okay, then finish it. Ah, you finish it.
At lower dosages, males and females both have like an equivalent reduction in cholesterol. So then as the dose increases,
Hmm. Hmm. Okay, good. Um, so in other words, right? So the third model, which I think Sahil said, was I can somehow combine this. So one way to combine this would be, let's see. Uh, okay, let's see how we combine this. Okay. Okay, does this model make sense? So this 1-0 thing, right? It's not because I'm trying to be sexist, but male and female M comes first before F. That's why males get a 1 and females get a 0. Or no, other way around. Sorry. Yes, I know. I will have to edit this out, but this is okay. I am not really controversial. This is what happens in R. F comes before M, so that's why F gets 0 and M gets. Sorry. Okay. With this model, what does this model collapse to actually? Does this make sense? Like, what is this model first of all? So let's do it for females. This will be what? It will be beta 0 times 0. It will be beta 1 times x plus beta 2 times 0. And for males, it will be beta 01 plus beta 1x plus beta 2. Okay? Is that what you wanted to say? Or something? Kind of. Okay, so this is one way to sort of collapse things, right? But you can see that this will be just that females have no intercept, they only have a slope. Males have an intercept, they have a slope, and they have another slope. Okay, this is partially incorrect, but we will come to what's the right model in just a bit. So the first thing, let's do what Sharadeep said, which is, or well, let's first do what I said, which is we can fit one single model for both of them, right? Which is you can just run one regression line and fit it. And again, there's nothing wrong about it as such, if you think about it, because well, it does capture the overall relationship, and that's what is being plotted here. I could fit one line which passes through both of them and it's all good. Okay, this is just separated based on the color. But we can see that if you notice, the slopes are actually different. I can allow for the simplest model that I fit here is very, very simple. I did not even actually have to explicitly fit a model. I'm just doing a geom line which fits one line for all the other, sorry, excuse me, 1 second. I did actually fit a model, but that was earlier. So the simplest model that I fit is a linear model, which is cholesterol as a function of dosage. Okay, this is the simplest vanilla model that you can fit. Then we can see that vanilla is because vanilla is vanilla, right? It is the simplest form of stuff. No, yeah, anything. Vanilla is. Oh, do I use it a lot? You heard it all. Vanilla is like the base. It's like a, yeah, the base flavor of a lot of things.
You agreed to this.
I think it might have been a concoction of the West, but it has stuck around. It is one of those things that has stuck around. Okay. Also, I think maybe like as the economy was growing up, we realized vanilla is. When I was growing up, if you got vanilla ice cream, that was the best. Like that's the only ice cream you had. But as we progressed, I think we have now access to different things. So vanilla has taken a. Does anyone eat here vanilla ice cream? No one, right? So that's what has happened. It has become that obsolete thing. I'm of that generation. That's why I can make.
But this is a great thing to think about because it's like the simplest model and you won't use it.
You won't use it, right? Like
It's
most
just
people will not use it. Most people don't eat vanilla.
But
You will not go like to go to well, Naturals doesn't have it, but any other ice cream shop will.
it will be available in wedding parties for free.
That's the first ice cream I had in a wedding party, which was vanilla ice cream. Right. This is about 2000ish. You had fridge at home, but getting if you had a family pack arrive at your home, that was a big thing. That was a celebration of something really, really big, and that was vanilla quality walls. If you have heard of that company. Okay. Um, So we're going to make some adjustments to this model, and we will change. We will allow for a different slope. So whenever I apply, whenever we add something, right? Remember that R by default will fix one intercept, right? So this model here by default has an intercept that's already part, which is beta 0. All I'm doing is I'm changing the slope based on the gender. And the way this works again is based on the overall predictions, right? So here, sorry, this went a bit far ahead. Okay. So here, if I print the model, I'm going to print the model which is here. There is only one intercept. Okay? This is one intercept, which is whatever it is, 203 point something. Dosage is minus, and then there is a term for gender male, right? So this is the slope that you have specifically for overall the entire. So the model that you're essentially fitting is y is beta 0, one slope, but I'm accounting for dosage, but I'm also accounting for gender. Okay. So in this sense, when the stuff is when the observation is female, this model simplifies to just this. But when it is male, I should use a different chalk color. This becomes beta 0 plus beta 1x plus beta 2. That shift that you're seeing. So the shift that you're seeing, we now allows us to plot slightly different models to begin overall. Right? And the reason this line is slightly off in this setting is because we have the observation there are slightly off, and that's why you see this. They have the same intercept, but a different slope overall for this model. Let me make a very small change, which is I'm going to ask it that there is no intercept anymore. So by default, R will allow for an intercept, but if you remove this effect, hold on. If I remove the effect, it now has a slightly different model, right? So it has a specific dosage term, of course, right? So there's a pattern that is coming because of dosage. And then now things have splitted based on gender, which is very, very similar to what you saw earlier, but there's no explicit adjustment that is being done for that particular gender, for that particular intercept, excuse me. Okay. There is another model where I can now allow for both slope and the or I can allow the slope to be a function of the gender. Here, things were still dependent on one term versus the other. Now, in the next case, what I'm doing is I'm going to say everything is so there is a gender term, but there is also what's called an interaction between the dosage and the gender, which means that the slope can change based on the final value that you see. They're allowed to change based on the gender, which was something which was missing earlier. Rather than fixing the dosage or the gender based relationship, this only allowed you to have a shift in some sense, right? So let me sort of go back and figure out what changed, right? So when you did this model which we was previously fit, we had beta naught as the intercept, but the corresponding shift that you saw was because of a change in the intercept, which is beta 0 plus beta 2. Okay, so there was a shift. That's why you saw in in this model, right? The slope moved up. It's still parallel. Right? Things are still parallel. You see this shift that has happened because of that extra beta 2 term. Now what I'm saying is I can see that maybe the slope also changes. There's no reason that the slope has to remain constant. And to fit that model, what I'm doing is dosage into gender. So if you do dosage, which is x, into gender, in terms of R, this is what it expands to. One intercept, one slope for x, one slope for gender, but one additional factor for the interaction between those two. And that's why when I plot this model, it's going to look different. Intercept is not just shifted, but also moved by quite a bit because this interaction between the male and the female, the male and the dosage and female the dosage is different. Does that make sense? So very different. Like of course, none of these models are like both of these models have their own advantages, but this looks like a better fit overall, even visually, which you can of course confirm by running AIC. I've not run it here. You should run AIC and do it.
So in this last model, the intercept is not changing.
The intercept is changing.
It is changing.
So let's expand that model to see what is overall happening. Okay. So the model that I fit now is beta 0. Okay. Now comes the interpretation part, which is what I want to you to focus on. So for females, tell me what the model will be.
We cannot do beta.
Correct. Fair enough. Okay. What about males?
Beta naught
Plus
beta 2 beta 3.
which is equivalent to beta 0 plus beta 2 plus okay. So intercept move, slope also move. But I want you to remember this because that's how you interpret the coefficients, right? So what is beta naught? Intuitively or in terms of explanation, what is beta naught representing in this context?
Intercept for beta.
But can you be a bit more descriptive? Intercept of what? Like what is it?
When dosage is 0.
Correct. So beta naught is the cholesterol level when dosage is of the drug is zero. Okay? Baseline. Exactly. That's the baseline. What is beta 1? Focus on that.
Sensitivity of change in cholesterol level.
Okay, change in cholesterol. So slightly more descriptive. So it is the change in cholesterol per unit change in dosage. Correct. Okay. Does everyone see why? It's the change in cholesterol per unit change, which is what how much does cholesterol drop by or change by. In if you change the drug usage by 1 milligram or whatever 1 unit in females. Why in females? Because this is what the model is telling you. It's only for females. Okay. Then what is beta 2?
Should it be average change?
It should be average. That's correct. So, yeah, sorry. This should be average. Everything here is average, actually. We're talking about the averages. Correct. Thank you for correcting me. Average change, yeah.
I have a doubt about the model. Instead of such a model, why do we not just decompose it into like take 1 minus g, 1 minus g, beta naught, 1 minus g.
Fair enough. Why not fit two different models to begin with, right?
Then you can just decompose and then there are 4 parameters. Would it be the same or would there be one?
Good question. Let's do that in the assignment. Okay. So, very good question, right? Of course, why should I break my head? Why I mean, intuitively, why should you break your head about this?
So it is so we can fit different models, but it is also telling us something more. So it is also comparing the male and female. If you fit them independently, how would you compare?
The comparison is dependent on the scale of the data that you have, right? So if you take the male data separately and female data separately and run two different models, um, interpreting the coefficients A from one model to the other one model is not as straightforward as you think. Yeah.
You just take one model and you in this model itself you multiply one minus g into beta naught plus one minus g into beta one, and then you have g, so you have the entire
Which is exactly what this model is also doing. Right? It's internally coded that way. That G is either 0 or 1.
here you will have the beta naught plus beta one.
Hmm.
So instead you can just have only beta naught and then you have a different beta two.
Okay, so you're saying that okay. I see. I think I understand what you're saying. So you're saying is this what you're saying? Some beta not dash 1 minus 3. Is that what you're saying?
Yeah.
Hmm. Okay. So the good thing is, well, genders are 2. So yes, you can do it. I give you um, 300 different categories now. Okay. So there are, let's say, 300 different classes in. I want to do this for different classes in IIT Bombay. There are 3 different classes. How would you go about it?
Wouldn't decompose in that case because then there will be some mean tendency of things.
So exactly right. So these models allow you to do that comparative analysis. There is a different approach where you say that while there are these 300 different models, I don't care about what individual effect is, and it becomes what you were saying, which is random effects. We will not cover random effects in this model, in this class. But broadly, the idea is that when you actually have data, you should deal with it at once. That's the power, because in this case the power actually comes from being able to look at all sorts of combinations. So right now I only have dosage and gender, right? If I add 5 more different variables, the combinations that you will have to test and fit the model on will become exponentially high. So if you start doing segregation, you will lose that power. That now I have, let's say, so I added dosage, but let me add height, let me also add weight, and let me also add whether the person is obese or not, right? So this is already blown up combinatorially in that sense. So you don't want to do that either, right? For
Can
that.
it not be a function like a continuous function which is just correlating one of the factors with the cholesterol and then combine those models?
You could run one round of correlation,
Yeah.
sure, but I'm telling you that this is after that also, right? As in, like, even after doing that, you find that okay, 5 out of my 10, which I think you probably are hinting to the assignment problem in some sense. Are you hinting at the assignment problem?
That's it.
It's due. Okay.
So with this model, it looks like so you were saying it's G and one minus G. It's not only so when you're saying G and
So yeah, so I think what his point was that if it is female, then it becomes just beta naught dash, okay, because G is 0, and if it is 1, then it becomes beta naught. So coding it that way, like coding it that way.
Yeah.
That's what you meant, right?
Yeah, you are talking. If this is there is two categories, it is somewhat like you can approach that.
Yeah. Sorry. Okay. Yeah. Finish.
If there is a continuous kind of weight and this kind of category like dependencies also, then you can create a continuous form of function and then fit that first.
Fair enough. You could do that. You could fit you could synthesize a new function from your 2 or 3 continuous variables and fit it. Okay.
can I explain what it is?
So what Subhakash asked?
Yes.
Yeah. So Subhakash asked if there is a continuous, if your variables are continuous, then rather than doing these kind of approaches where you're multiplying things x versus g, x into g, you can synthesize a new function which is basically x into g and make this one of your variables and fit that over, which is fair. You can do that actually, right? If you don't care about their interaction, right? So what is the power that is coming from here, right? Like the power that you're getting from is what is that differential between male and female that gets added. That
The
is,
interaction is somewhat missing if we do it independently.
yeah, the interaction is going to miss out, right? So that's what I think Ashwari started to motivate, in the sense that you can see that the slope itself is a function of the female or the gender status, right? So there is an interaction. That's the interaction term that is important. And like this, I also learned very late in life, but it's very powerful. Like that lens of being able to look at that there is interaction is very powerful. So that's why I wanted to help me interpret the rest of the term. So we were at beta one. What is beta two? I will write it here. I will write it. Yeah. What is beta two? Sorry, where is the model? Yeah. Okay, that's the model. Where is beta? What is beta two?
It is the amount in baseline shift.
Cholesterol level of male minus female.
Okay. So, huh.
Cholesterol level of male minus female.
Okay, slightly more nuanced. Like it is the average cholesterol level. Is it change? It's the baseline shift in males versus females. Okay, did I write females here? Ah, okay. This is also important. This is in females.
Yes, it's written.
Is it written there?
Last line, dosage in female.
Now this is for beta 1, but I think this is not correct. Otherwise, this stuff. Sorry for messing this up, but it's the cholesterol level when dosage is 0 in females. Okay, and this is cholesterol level, average cholesterol level when dosage. Okay, now this is more pronounced. Okay, this is 0. What is it? Average cholesterol shift in males. Average cholesterol shift or difference, whatever you want to call it, in males as compared to females. Okay. What is beta 3? What is beta 3?
The shift is shift in this.
Yeah. So slope again, we can make it more nuanced, right? So in the sense that this is the average change in cholesterol levels of males as compared to females for the same change in dosage levels. Does that make sense? So I'm changing the dosage level by 1 unit, for example. This is the extra change, average change in or average extra or over or whatever under change in males that is happening for the same dosage change in males and females. Okay, is that clear? That is what the interaction term is. So this term beta 3 is extra. Beta 1 is there in females as well. So there's a slope of dosage. When this changes by 1, x changes by 1, how much does this change by? Beta 1. If x changes by 1, how much does this change by? Beta 1 plus beta 3. So it's the extra or the over change or extra change in males as compared to females for the same difference in dosage. It's how much amount of cholesterol is extra or under. I don't care about it right now. That changes if you change the dosage by 1. Okay, fair enough. Any questions?
What if the lines are parallel? Beta 2 and beta 3 will be similar.
Yeah. So if good question, right? So in this case, when you had this model, right? So if you have this model, what you have is like the slope is the same. So your beta 3 goes to 0, right? And your intercept is correct. This shifts by certain thing. So this is that extra thing that you're actually accounting for in the interaction effect. What is the difference in slope for males and females when once you add this to? And the way you are able to capture this is because you're allowing for the slope and the dosage and the sex to or the gender to interact. Okay. Any other questions? Okay. We will. Any other questions? Please ask me now.
but regarding the previous answer,
Yeah.
so you said that mu and the variance that is independent in case of the Gaussian.
Yeah.
But when we derive the variance using the
Fair
logarithm,
enough. You have to account for the mean. You have to input it. Yes,
so
that's right.
then it becomes dependent, right?
Yes, that's correct. So in when you're actually deriving it in terms of what is your variance as a function of mu, then yes, but you're working with not mu x bar, right? So your x bar has a dependence on your s square, of course. But by definition, how much spread you have in a Gaussian is not a function of how much what is its mean, right? So I can give you a mean of 5 and I can ask it that simulate it with sigma equal to anything. I don't have to constrict you. But if I give you a Poisson of lambda equal to 5, you whatever you do, your variance is going to be 5.
So mathematically, formula wise, it is dependent, but theoretically, it is
No, it's dependent because you're doing MLE, right? So your MLE estimate is dependent. That's where the dependence is coming from. That you need to estimate x bar to get to, or get the best MLE for, or the MLE for x bar to get the MLE for s square, right? So that's where the dependence is coming. Okay, this slide just kind of tells you exactly what we did, right? So I don't have to cover it anymore, but yeah, make sure you understand this because this is very, very important from an understanding point of view. Okay, this is just a difference between what question Sainath asked, which is what is difference between the model that we fit earlier and what model that we fit now. The coefficients we already discussed, so I'm not going to repeat what is written on the slides. Uh, Hopefully, all of you understand it. Okay, unless you wanted me to discuss this. Okay, now let's start the fun part, which is dimensionality reduction. So I think some of it will bleed through the next lecture, which is fine. We might do the hands-on again on next Wednesday. So the question that we want to understand is there is this family health survey data which got put out in public, where there are 131 different variables. You've already, those of you who have touched the assignment would have seen this version already, where there are different metrics of what is being measured. Different questions. What is the female population age 6 years and above? Population below 15 years. What are they eating? Do they have hypertension? Do they have diabetes and so on? Like there are 131 such variables measured in both rural but plus urban settings, and that's what your NFHS 5 urban stands for. The question that we're trying to ask is, there's too much data here, 131 variables, which is not a lot, but still a lot to visualize. So the first question that I want to ask is there a global structure in this data, in the sense that this data is measured using different states? Does that, when I measure this across all states, of course there will be something that I can learn about India, right? Like I can learn whether are certain states overall clustering together, are they showing something similar, or are they performing different or similar on certain metrics? And what are these metrics? We will try to decode. But my question is that if I gave you this data of whatever 20 plus states in India and ask you to figure out that what is it that data telling you, right? So one approach that you will take is you will take one variable at a time and start analyzing it. The other approach is, what we will probably do is we have, let's say, variable 1, 2, 3, 4, and you have states. This is state 1 to state 26. There's data here. Should maybe perform some sort of clustering, right? So our goal here is to figure out, in some sense, in a very poor man's way, that what is the structure in this data, right? Like how are they correlated? Are they correlated at all or not? Is the question clear? So very simply, the way this is often done is using what's called principal component analysis. Right? So to motivate principal component analysis, I will just give you an example, which is I've given you a data which is a two-dimension, which is 4 points. I want you to give me a one-dimensional representation of this data. Okay. Right now, I'm seeing this in 2 dimensions. I want to see only one dimension. However, you can do whatever you want, but the whatever you do, if you give me one dimension, which is this, whatever, I want that dimension such that if I wanted to reconstruct this from that one-dimensional data to again back to this 2D picture, I should be able to do it very accurately or as accurately as possible. Is the problem clear? That from a 2D picture, from a 2D coordinate system where there are 4 points, I wanted to give me a one-dimensional representation of this picture so that I only look in that one dimension and I should be able to still differentiate them. But if I want to reconstruct this, I should be able to do it. Problem is clear? It's a geometry problem, like or intuitive problem. I'm not looking for any mathematical proof, anything. This is intuition. What picture? Where should the line be? One dimension needs one line, right? So should it be this? Should it be this? Because if you give me just this, right, and some representation along that direction, that's the only direction where I will see, and I will see that this point is different from this point, is different from this point. Which line would you recommend?
X1 line.
Okay, why x1? So let's say I delete x1, I delete x2, and I keep only x1. But then you lose this information, right? You everything has to then. So when you draw a line like this and take the point there as your point, okay, fair enough. So he's saying, Samir is saying you can drop a perpendicular from this. Whatever point you get here, you only take. Then I can just visualize those points, right? So in other words, his one-dimensional data will look like this. Now from here, I want to reconstruct this figure. How would you do it?
What it is basically projection.
Hmm.
You just basically project back the image.
Okay, so how would you project that?
So this is a perpendicular distance.
So you'll keep the perpendicular distance. as well.
Yes.
You have to keep the original distance.
Yeah.
in some sense. Okay, fair enough. Is it the best possible reconstruction that you can do of this?
If we are keeping that, then we are not used that.
Yeah, we have not actually retained the information. Right? I want to do this because I don't have big storage. I want to be very sparse. I don't have way to store this 2D data. I don't have way to store extra information. I want to do it in a very totally unsupervised way.
Or maybe just polar coordinates will have the same kind of details, right? Similar amount.
Okay, polar coordinates. Okay. Yeah. What's your name?
Crucial.
Rushid. Yeah.
Choose the line with maximum.
Okay. Why? Why maximum variance?
Also that you can capture more information on the line.
Okay, fair enough. Which year are you in? Fourth year. Okay. So you have seen some version of this stuff, which is fine. Of course, which is fine. Good. That's a good answer, right? So we will see why variance is actually information, right? So when you project, right? So like I can draw a line anywhere here. Like I can draw here. Flat.
Just on this, like just out of interest. So this version, yeah, you said you were storing weights.
I would have to store weights if I want to
So
reconstruct.
in case of PC, you are storing weights, like it's not different. If I were to argue that something.
Okay, why, how am I storing this?
So you are getting those eigenvalue vectors. So those are, how is it different from this? I think this is an easier version. Like at least in this case, this is better than.
Fair enough. That's fair. If you can store this, then that's fair because then I all have to do is
Yes.
go just
At least in this case.
Fair enough. That's fair. Yes.
So, like to reconstruct, I recall that if you have the eigenvector which is supposed to capture the maximum variance, then we can actually calculate the error that is the perpendicular. That is what is.
Yeah. I'm cheating a bit because I'm not like everyone here is using terms which I've not even introduced. So I will introduce this in just a bit. But that's correct. What you said is correct. Okay, so this is your, of course, you can project the data into lower dimensionals such that the reconstruction error is minimized, right? So, for example, this is one of the possible ways to do that projection. I take this line here and project all of them. Projection is nothing, but you draw a perpendicular from that point to this line, and these are the points that you get. Right now, this is the only axis I have captured. I would like to use this to reconstruct my data. This is what the data looks like in my one dimension. So if I wanted to reconstruct this, the best possible, if I don't store the weights, then the best possible way for me to do it in a sparse way is to rotate it based on what axis I took it, right? And you would have lost some information in that process. Why? Right? Because you started from here, and the only thing that is stored is because well, I chose the axis, so I know I'm not measuring anything other information. I chose what is this direction. I projected them, and if I want to now reconstruct this in 2D, this is what your 1D representation. If I want to reconstruct this, I'm going to just rotate this to this angle which I initially proposed. So I'm not storing these things as such because that's extra information. But in this case, I'm just storing that one extra information, which is what is the angle I began with. Okay, but it's not doesn't look as good, right? Like it doesn't look that you've done a good job of being able to reconstruct the entire figure. This is the figure that I wanted to reconstruct, but this is the figure that I'm getting, right? So how to do that? We will try to flush it out, and some of these slides are going to be slightly heavy. The goal is that even if you don't understand this, you should be able to understand the rest of the class. And I will not quiz you on this stuff because this is slightly more technical. But just to give you an idea of what is important, right? So there is a concept of what is called vector spaces. Vector spaces are nothing but anything that you want to represent. You can represent them. This is of course 2D. I cannot visualize. I cannot draw 3D, or I can try to, but beyond 3D, I cannot go any further. But I can represent each of these dimensions as some unit vector, right? So this is x is 1, everything else is 0. In this case, x is 0, y is 1, everything else is 0. That's what your basis vectors is, right? So the basis vector allow you to capture all the dimensions that you have. This is so in a standard basis vector of R2. What is R2? It's just a two-dimensional sphere. Any point in this sphere can be represented by a combination of 1 0 and 0 1. You can combine it in all possible fractions, and you will be able to construct this particular circle, right? That's not very hard to understand. All you need is like how much should I add this and how much should I add this, and you will still lie within the circle as long as you're normalizing for certain factors, which we will cover in just a moment. So the concept here, the reason this works is because these two vectors are what's called orthogonal. So they are perpendicular to each other. So whenever things are perpendicular, or whenever their dot product is 0, x dot y, this is x, this is y. Even if you don't know dot product, don't worry about it. It's basically saying that the angle between these two is 90 degrees. Okay. The orthogonal basis is a set of basis vectors. These are called basis vectors because they help you create the entire space. So they are the basis of that space. You can have orthogonal and non-orthogonal basis. We will focus on orthogonal basis only. Okay? These are perpendicular to each other. And then you can have an orthonormal version of this. The only difference between orthogonal and orthonormal is that the norm or the magnitude of that vector is 1. So in this case, I can have this vector even if its magnitude is 1, even if its magnitude is 10. The direction will remain the same, the magnitude can change. Orthonormal has a vector which is of dimension, which is of magnitude 1. Okay, this slide is clear. Okay, so if that is clear, this should follow. Now you're in good space. That's the only sort of slightly technical slide that we will cover. But this is a way to visualize this, right? So as I said, this is a geometric problem or a logical problem, not a hard problem. Imagine all your data is centered around 0. Okay, so the overall mean of this particular entire data set is 0. I can draw a vector. This tells me what is the distance between from the mean. This is mean is 0 to this, which is t. This is your original point. I am looking for some random direction of the vector, which is happens to be this. I drop a perpendicular from it, and this is the point that you get x bar bar or x parallel. This amount, right? So what point was here is now here. So this error is called a reconstruction error. If I want to reconstruct this point, since I'm going to retain only one axis, I will commit this much amount of difference overall. This is the amount of variance that you have because this is mean centered and the difference, how do you calculate variance is y minus y bar square. So that is what your um, once you get the vector, this is what the amount of variance that you have for the projected points, right? So for the projected points, the variance can be quantified by just measuring its distance from zero and squaring. Does that make sense? So overall, if I want to minimize this, right? I want to minimize this. This is your reconstruction error. The way to minimize this is to keep this point or this line as close to this point to begin with, right? So I should rotate it all the way till here. And in the process, what I've done is I've minimized this, maximized this variance, right? So when you collapse this, your R becomes zero, and if your R becomes zero, your variance is maximized of the projected points. Does that make sense? Does that idea make sense? Okay. So that's what is done in the case of PCA, right? You can have chosen a some slightly different axis, and of course you can see here that you're doing slightly worse in this particular axis. Why is it this axis and why not this axis? Is because if I do this, then the reconstruction error is maximum is larger in this case. I want it to be as small as possible, and that's why that particular axis visually is better. Okay. So the goal is that now I told you, I forced you to think that this is the correct axis and maybe this is not. Now our goal is to formalize this, right? So y is minimizing the reconstruction error, which is equivalent to maximizing the variance of your projected points. How do we look for this direction? That is our goal. Okay. Why are we doing all this, right? The reason we are doing all this is because I want to visualize what the states look like in terms of their different variables. There are 131 plus variables. Now those 131 variables are too many. I cannot never put them. I can never visualize them in a 2D picture like this. So I somehow want a way that if this idea works in two dimensions, can I generalize it so that it works in those higher dimensions, 130 plus dimensions, so that when I reduce those 131 dimensions and only visualize two, I should be able to see the structure. Okay. So that's what I think. This is a good stopping point because the rest of the talk will again have to talk about covariance. What I want to show you quickly is where are we headed, um, right? So overall, like just to give you an intuition of what is happening in the technique that we're trying to figure out, is imagine you had this axis, this different version of points which are distributed in 2D, and I'm looking for that. What is that one axis of variation where if I use this data, the overall information is maximized or the reconstruction error is minimized. That happens to be this axis, which at this point, when it comes here, for example, you will see that the points are the most spread apart, which is equivalent to maximizing the variance of the projected points but minimizing the reconstruction. Right? So the point, the moment the line actually comes parallel to this or overlaps this green axis, that's why you will see that overall these shrink. The reconstruction error overall shrinks. So we'll discuss in the next class how we reach there. We will do an exercise talking about what happens if you run this kind of technique on the states, the national family health survey. I will ask you to decode what pattern you see. Right? But this is where we want to go. We want to go from 131 dimensions to two dimensions only, but by retaining as much amount of information as possible. Okay, I think we'll stop here today and we'll continue with the next class.